Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler and today we're going to be doing Unit 2, Lesson number 6 on one-to-one functions and inverses. As usual, in these introductory units, this is a review topic, so if you need sort of brand new information on one-to-one functions and inverses, you'd be best served by looking at some videos in Algebra 2. Alright, let's jump right in and discuss what a one-to-one function is. Now functions are often categorized. Linear functions, right? Even and odd functions, quadratic functions, trigonometric functions, right? We categorize them by shared characteristics. And one-to-one functions have a very, very important characteristic. Let's take a look at their technical definition. A function f of x is said to be one-to-one, sometimes abbreviated like this, one-to-one, if x1 not equaling x2 implies that f of x1 doesn't equal f of x2. In layman's terms, different x's give different y's. Now, a lot of times people confuse the definition of a one-to-one function with simply the definition of a function. Remember, a function just says any given x value must have at most one y value. What this one says is different x values have different y values. All right, let's take a look at exercise 1. It says, which of the following graphs illustrates a relationship where y is a one-to-one function of x? Explain. Well, think about this a little bit, and then let's talk about it. All right. Well, let's take a look at exercise 1. Exercise 1 is most certainly a function, but the problem is it's not a one-to-one function because if I were to draw in this horizontal line, I don't know, let's say it's y equals 3, then there would be two x values that would have the same y value. But one-to-one functions, there must be different y's for every x. Now number 2, if I drew in horizontal lines there, each y value would only be hit once. But the problem is that's not even a function, right? That's not even a function. So clearly that one's not right. Number 3 is all sorts of problematic. It has both repeated x and y values. In fact, our correct choice is choice 4, both because it is a function and it is also a one-to-one function, right? Now, what I was using in this particular choice was what was known as the horizontal line test. As my students know, I'm not big fans of these tests. Right? But the horizontal line test says if you've got a function, so you have to start off with the function, so number 2 is already out. But if you have a function and then you draw any horizontal line, it can intersect the graph of the function only once, or better yet, at most once, in order for it to be a one-to-one function. The reason that works, of course, is that along a horizontal line, the output is always the same. Y equals a number. Therefore, if it hits the graph more than once, such as exercise number 1, then the same output got repeated. Okay? Anyhow, I'm going to clear this out, so write down anything you need to, and then we're going to move on to exercise 2. All right, here we go. All gone? Let's keep moving on. Exercise number 2 just asks a very simple question. Is the piecewise function defined by the formula f of x equals, and then you can read that piecewise formula, is this a one-to-one function? Justify your answer. And let me just say, before you start leaping into this, that it's perfectly okay to graph the function and think about the horizontal line test. But let me challenge you to try to not do it with the horizontal line test. Try to come up with some other way of doing it. We'll talk about both eventually. But pause the video now and see if you can figure out whether this is a one-to-one function. All right, let's talk about it. Now remember, ultimately, it's not about horizontal lines. It's about different x's end up giving us different y's. All right, that's what it's about. So one of the cool things about this is I can easily show that it is not a one-to-one function by finding two x values that have the same y value. Watch. Let's say f of 5. Well, what is f of 5? 5 falls in this category, and its output is 1. So f of 5 is 1. I could also do f of 10. Well, f of 10 also falls in this category, and so its output is 1. And therefore, no, right? Different x's gave me the same y's. Now, if you really just feel like you've just got to do it with a graph, here's the graph. All right, and again, I'd highly suggest trying this without a graph. Do a little dimensioning, 1 and -1. What does it look like? Well, it looks like the horizontal line y equals 1 over here. And then it looks like the horizontal line y equals -1 over here. And so obviously it fails the horizontal line test because a horizontal line there or there will hit the graph more than once. All right, well, pause the video now if you need to before we go on to the next problem. Okay, I'm going to clear out the text. Now, exercise 3, and then I've got actually a picture from the next page, asks a very, very important question. Why are one-to-one functions important? Now, for those of you that go on and study higher level math, one-to-one functions are important for a lot of different reasons, a lot of different reasons. But there was one reason more than any other that you learned last year in Algebra 2 with trigonometry about why they're important. Pause the video now and see if you can remember anything. All right. Well, from last year, one-to-one functions are important because they have inverses that are also functions. Now, some math teachers will say this incorrectly. They'll claim that only one-to-one functions have inverses. That's not true. All functions have inverses. All functions can be invertible. The question is whether or not the inverse of a function is also a function. So let's take a look at this mapping diagram. Now, this is on the back sheet of the worksheet, if you're following along on the worksheet. Let's take a look at it, all right? Now, what we've got here is what's called a function mapping diagram, and it's really kind of cool, right? So just for a minute, just for a minute, let's say that this wasn't here. All right, we'll come back and we'll erase it so that it is there. And let's say that we put A into F, and what came out was D. And let's say we put B into F, and what came out was E. And let's say we put C into F, and what came out was E. Now, there's absolutely nothing wrong from the perspective of it being a function, right? Nothing wrong at all, right? You know, because look, each input has just one output. It's not a one-to-one function because B and C, which are different inputs, gave us the same output, E, right? The problem is if we tried to reverse the process, let me do that in red, right? If we tried to go back this way, right, then what would happen would be that an input of E would have two outputs, B and C, would have two outputs. And that's not allowed for functions. Right? That's not allowed. Okay? So in order to have a one-to-one function, right, the x's and the y's, they kind of pair up, right? For every x, there's a unique y, and for every y, there's a unique x. So the idea of inverse functions is really simple. If A goes into F, and it gives you D out, then when D goes into what's called F inverse, it gives you A out, right? Likewise, when B goes into F, it gives you E out, and when E goes into F inverse, it gives you B out, right? C goes into F, it gives you F, and when F goes into F inverse, sorry about that, it gives you C. Okay? What's really cool about inverse functions, not their notation, we'll talk about that again in a moment, but what's really cool about inverse functions is they just switch the roles of inputs and outputs. So the domain of F, right? The domain of F becomes the range of F inverse. And the range of F becomes the domain of F inverse. Everything just flip-flops, and it makes sense because all a function does takes inputs and gives you outputs. So there's no reason why we couldn't suddenly say, hey, let's make the outputs the inputs and vice versa. And that works great as long as the original function is one-to-one. Now, a little comment on the notation, okay? And hopefully everybody understands this carefully. It is unfortunate that this is the notation used, but f inverse in no way, shape, or form will ever mean 1 divided by f of x. It has nothing to do with division. It really has nothing to do with exponents at all. It is simply a shorthand way of saying to do the opposite of what the function has done. Okay? So we're going to clear this out, and then we're going to talk a little bit more about inverses. Pause the video now if you need to. Okay, here we go. All right, exercise number 4. Easy, but very important. For a one-to-one function, y equals f of x, it is known that f of 8 equals 2. Which of the following points must lie on the graph of y equals f inverse? Think about this for a minute. All right, well, think about it. Right, what happens in the original function is 8 goes into the function, and what comes out is 2. And what that means is that the point 8, 2 is on the graph of f of x. On the other hand, what's going to happen with the inverse is 2 is going to go into f inverse, and 8 is going to come out, telling me that the point 2, 8 lies on the graph of f inverse. Now that's an important problem, because even though it's very easy, it's very important because it really is the key to how we graph inverses, right? So if I have a graph of a function and I want to know what the graph of its inverse is, all I have to do is take all the x, y coordinate pairs and just switch them. All right, that's it. And then I regraph. So it's pretty easy. All right, pause the video now, write down what you need to, and then I'm going to clear out the text. All right, here it goes. Stray mark there. Let's take a look at exercise 5. I love this one. Now, this is a very deep question, but let's take a look at it. On the June 2011 Algebra 2 with Trigonometry Regents exam, so this is in New York State. If you're watching this video from some other state, this is on the New York State Algebra 2 with Trigonometry Regents exam, so the state exam. The following question was given. If f of x equals x squared minus 6, find f inverse of x. Letter A asks, why is this question poorly written from a mathematical perspective? Think about that. You're actually critiquing the question. Pause the video now and think about it. All right. Well, it's a poor question because f of x is not a one-to-one function. So its inverse is not a function. Yet, the question implies it is. And why? By using function notation. I'll never forget this question. I wasn't even the head of the Arlington math department at the time, and yet I still called New York State while we were grading the exam, and I talked to some poor, probably grad student kid sitting in a room who was just like, no, man, we never told you that the inverse was a function, so they recognized that it wasn't a function, and I said, but you use function notation. Oh, well, that notation can be used for things that are functions or not functions. You know, and I said, okay, find me a textbook that does that. And of course they couldn't, because it's not a function, right? And they shouldn't use function notation for it. But getting past that, let's talk about letter B. It says, how can you restrict the domain of f of x so as not to restrict the range, but that creates a one-to-one function? So one-to-one functions are so very important because inverses are important. And inverses are so very important that sometimes we'll take a function, like the one that we have right here, And we will restrict its domain. We'll cut its domain down, right? Because the domain of this function, that's all real numbers, right? But we'll cut it down as much as we can to restrict the domain so that it's now one-to-one, but not restricting the range. Now, the key to doing this is really understanding graphically what's going on here. All right, so there's my y equals x squared minus 6. Now, what I want to do, right, okay, the domain is currently, right, all real numbers, okay? And the range is y greater than or equal to negative 6. What I don't want to lose is this guy, okay? But I'm going to play around with that. Now, there's two ways to restrict the domain, right? So we say, no, not all real numbers anymore. We're going to cut that thing down. There's two ways to restrict the domain, and we want to list them both so that the range is still preserved. Pause the video and think about that for a minute. All right, well, let's talk about it. It's pretty much this simple. Let me go in a different color, right? I could say, well, take every value of x over here. Take all values of x such that x is greater than or equal to 0, right? That'll do it. So that's one restriction, right? Or I could say, nah, I like this part of the parabola better. So I'll go x less than or equal to 0. So these two restrictions on the domain make the function one-to-one, right, and preserve the range. Now, letter C says, find f inverse for each of the domain restrictions in part B. Well, let's go back to blue, and let's actually just solve for the inverse. Okay, now the way that we solve for the inverse is that we switch x and y. That's sort of step 1. And step 2, we solve for y. So let's do that. Let's kind of be ignorant a little bit. Let's just switch x and y. Right, so I'll get x equals y squared minus 6. Add 6 to both sides. And then take the square root of both sides. Now that gives me 2 answers. Y equals plus or minus root x plus 6. Now which one goes with which? All right, now this is some wonderful logic. So especially if you're one of my students, I do expect you to really, really grasp this logic, okay? So let's play around with it. All right, we've really got two functions here. We've got f of x and we've got f inverse of x. Now, when we say that x is greater than or equal to 0, right, that translates in f inverse to y greater than or equal to 0. So which one of these two formulas, right, we have y equals positive x root x plus 6 and y equals negative root x plus 6, which one of them has y values that are only positive? Well, it's this one. This is where it's yet again very important to understand that I'm only getting one output there, and it's a positive output. So the correct f inverse for this restriction is root x plus 6. By the way, graphically, take a look at it, right? Root x plus 6 is this, right? And if you remember, inverses are symmetric across the line y equals x. So here's one of them. Oops. Sorry about that. Let's go green. All right, obviously green is going to be the other one, but if I have a function and I restrict its domain to being x less than or equal to 0, what that's going to do is restrict the range of its inverse to be y less than or equal to 0. And the correct formula for that will be negative root x plus 6, right? Because this only has negative outputs to it. Again, just giving you a little perspective, that would be this curve. This one's a little bit harder to tell that it's the reflection of this thing across y equals x, but it is. I feel like the reds are easier to tell. So that's very tricky, right? The key is when we restrict the domain of the original function, we're actually restricting the range of its inverse. That's how you can tell which formula goes with the inverse. All right, well, pause the video now and write down anything you need to. All right, let's clear out the text and finish up the lesson. Okay, well, today we reviewed two important and very much linked topics, the topic of one-to-one functions and inverses. One-to-one functions are those special types of functions where different x values always result in different y values. Inverse functions are those functions that reverse the process of the original function. So inputs become outputs, outputs become inputs. There's lots of different things I want you to be able to do with inverse functions. I want you to be able to come up with their formulas. I want you to be able to produce their graphs, right? And very often, we're going to want to do more higher level things, not in this lesson, like identify their intercepts, their asymptotes, and their turning points. All right. For now, though, let me just thank you again for joining me for another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler. Until next time, keep thinking and keep solving problems.